We're going to start off by having a look at the free body diagrams from yesterday, because before you can do word problems, you have to be able to sort of analyze the question and come up with a free body diagram. So let's go through this. I know there were some questions that caused a little bit of, shall we say, discomfort for people, but that's good. A book is at rest on a tabletop. Diagram the forces acting on the book. I started you off with a nice easy one. Weight force and normal force. Can I safely assume that everybody got that? This is the worksheet from yesterday, not the one that I just handed to you. This is the worksheet from yesterday.
Today?
Yesterday, as the Beatles once sang. A girl is suspended motionless from a bar which hangs from the ceiling by two ropes. Diagram the forces acting on the girl. Well, once again, there's going to be gravity. Is there a normal force? There is not. Why is there not? There's no surface here, right? There is tension, right? Can you feel the tension in the air? Now it says two ropes. The actual diagram shows it like this. And I guess technically, if you want to be absolutely correct, those should be each half the length of that one, because those two together would have to add up to the weight force. Like, in other words, if this was 5 centimeters, those would have to each both be 2.5. I'm perfectly all right with you saying weight force and applied force, okay? At this stage. When you get to grade 12, if I'm asking you about the tension in each rope, well, then that's another matter. Like, for example, if her weight is, how much was mine from yesterday? Like, let's say it's me. Anybody remember how much I weighed? I think it was approximately 750 newtons, right? So how much would each of the rope have for tension? Each one would be 375. Each one. Okay, that's sort of a grade 12 concept, which isn't too challenging. An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it falls. Neglect air resistance. There is no air resistance. There is a weight force, and that is all. That's all there is, right? A flying squirrel is gliding. No wing flaps. In other words, he's not flapping. He's just sort of gliding like a parachute kind of thing. From a tree to the ground at constant velocity. Consider air resistance. Diagram the forces acting on the squirrel. Well, just like the egg falling out of the nest, there's going to be a weight force. In this case, it said neglect air resistance. In this case, it said there is air resistance, and it also says that there is constant velocity, which means that the forces have to be, the net force has to be zero, it has to be balanced. And so you've got an air resistance. I'm going to just call it a friction force that is up. Is the squirrel moving sideways? Could be, don't care. The arrows only show forces, they do not show motion.
Squirrels never flap their wings, is it?
Yes, they don't have,
Never.
they're not flapping wings.
Not even wings.
A rightward force is applied to a book in order to move it across a desk with a rightward acceleration. Consider friction. Neglect air resistance. Diagram the forces. So it's on a surface. So we have a weight force. It's on a surface, so we have a normal force. The rightward force is applied. It has an acceleration. There is friction. So I'm going to show a little bit of friction backwards. And my applied force, I would like you to show, considerably larger than the friction force. Clearly larger. That implies that there is a acceleration, right? Nod, yeah, good. Okay, exactly the same thing, except this time it's with a constant velocity. So the only difference is what? Weight force, normal force, friction force, and the applied force should be the same as the friction force. The applied force and the friction force have to be the same length. Okay? In this case here, what's the net force equal to? Which means the acceleration is 0. I thought you were going to show me. Number 7, a college student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. The vertical forces. There is no surface. There is only a weight force. It's one strap, so a single tension force. FT, or if you prefer FA, I'll take either one. Right? Tension force or applied force. What about the skydiver descending with a constant velocity, considering air resistance? Well, you have to consider air resistance if it's constant velocity, because that's the only thing that's going to actually cause it. So it's weight force and friction force. Once you get into these, they're pretty easy, are they not? A force applied to the right to drag a sled across loosely packed snow. Remember what I said yesterday? That's code for? There is some friction. With a rightward acceleration, diagram the forces. Weight force, normal force, a little bit of friction, rightward acceleration, big giant applied force. Number 10 is the one that always causes arguments.
It's only, you're only measuring when it goes.
Am I done? Cody says no. No, Cody? What else do I have to show? So you want me to show like something like this? That's what you want? How many people have something like that on the sheet?
I guess that's wrong.
Afraid so. An object in motion stays in motion after having been booted by the punter. Allow me to demonstrate. I'm not going to find it. Can you catch Sean? Yeah, I'm going to throw Sean this volleyball here. What we're talking about is when the ball is at its peak, when it's like right over Lloyd's head kind of thing. Don't worry about it. I'm a trained professional. When it's over Lloyd's head, am I applying a force to it? Unless I'm a Jedi Master. Not happening, right? When it's hanging in the air, when it's right here, up Mitchell Lloyd's head, I have no way of applying a force to it. The only force acting on it is gravity. An object in motion will stay in motion. An object in motion will stay in motion. I do not need this because I have already booted it. I've already thrown the ball. You do not need an arrow showing motion. The arrows do not show motion, they show forces. And the reason that people get confused is because if we go back to here, right? Back to this one here. Well, how come that looks exactly the same? How come the egg free falling from the nest looks exactly the same as the football, the football going through the air? Because it's exactly the same motion. The only difference being the egg is just that initial velocity, whereas the volleyball, I'll throw it to Lloyd because Sean's not listening, right, has a different initial velocity. But the forces acting on it are exactly the same. Nod and say, I get it.
I get it.
Do you really get it?
Yeah, I do.
Have I just asked you that same question that I've been asking over and over again? I have, right? I got to keep hammering that home. It's the same question, really. It's the is it moving? What are the forces acting on? It's do you really believe that an object in motion stays in motion? Do I need a force to keep the football moving? An object in motion stays in motion. If you wanted to really argue with me, I would allow you to say that there is a small friction force like that. A small amount of air resistance because the ball is traveling through the air. That's supposed to be a little area. Okay, there's a small amount of friction force. That would imply that there is a rightward motion, but you do not need an arrow like this showing upward motion. It's not. These are not arrows showing motion. These are arrows showing forces. How many people think you're going to see a question kind of like that on the test? If you put your hand up, you would be right. Will I ask it just like that? No. I will ask it in a way that determines whether you truly, truly understand or believe it. Okay, Sean, a car is coasting to the right and slowing down. Diagram the force acting upon the car. It's coasting, which means the engine is off or the gas is off, right? We have cars traveling on Earth, so we have our weight force. We have a normal force. It's coasting to the right and slowing down. It's already moving. Do I need an arrow going to the right? No. The only thing that's causing it to slow down is friction, like so. Nod and say, I get that. Is that not almost the same as the football one? The only difference being the football's not on a surface, is it, right? Yeah, same idea. Do you have this sheet that I handed out? If you wandered in late, you might not have it. So today is a big day. Today we're going to look at some sample of Newton's law questions. Pretty straightforward. Basically we're going to be using F net is equal to MA and F net is equal to FA plus FF. I call F net is equal to MA, I call that the bridging formula. And have I talked about this already? Maybe a little bit, no? Okay. F equals MA is the bridging formula that basically allows you to go F net equals MA. Anything to do with forces, like friction, components, all sorts of things, some that you're going to see in grade 12, all of that, the only way to get to the kinematics, you don't need to write this down, the only way to get to kinematics, like V bar equals D over T and A equals delta V over delta T, the only way to get to distance, to get to kinematics, you have to go through F net equals MA. It's the bridging formula that takes you from dynamics, the forces, to kinematics. Okay? It is truly the most important formula. Probably the easiest one too. Okay? But that's what we're going to do today. So we're going to start with that. Okay? In the next day or so, I will be giving you the Rampton flowchart. Former student Tyler Rampton put together a flowchart that shows every formula in grade 11 and how they all fit together in a big puzzle. It's a wonderful piece of paper. Okay, so, pardon me?
Named it after him.
I named it after him. Of course, he made it. He should get all the credit for it. It's up on the wall there too if you want to have a look at it. Okay, I will give you your very own copy. Maybe someday someone will make one for grade 12. No one's done that yet. Okay, so you've got the question here. Let's have a look at the solution. A constant force acts on a 12 kilogram mass and changes its velocity from 4 to 18 in 3.5 seconds. What is the force? What is the force? I'm solving for F. I don't know my F. I do know my mass. It's 12. It changes its velocity from 4 to 18. What would you call 4 and 18? What variables are they? They're both V's. Final and initial, exactly. The initial is 4. The final is 18. And I also have a time of 3.5 seconds. And I'm asked to find the force. The last formula is going to have force in it. You sort of got to work like backwards, right? If I write F net equals MA last, because I've got M, to get the net force, to get the force, I'm going to need to know the acceleration. So now I got to go backwards. How can I find acceleration? Yeah, delta V over delta T, right? Is acceleration. Do I have the T? Do I have the change in velocity? Not yet. I got to go backwards. You see how I'm working backwards here? Now in time, as you get better, you'll sort of see that route ahead of time, and you'll know you'd have to start there and then work this way, right? But it may help you to start on the right-hand side and write your formulas backwards. And I'm begging you, write the formulas. Already you can see there's 3 different formulas here, 3 different steps. This question is going to require 3 marks, 3 steps. If all I see is numbers scribbled on a page, I have no idea what your process is. Okay, so delta V equals VF minus VI. Final is 18, the initial is 4, giving me a delta V of 14. Right? And now I take that delta V, and that can go in there for that one. So A is equal to 14 over my time, 3.5. 14 divided by 3.5. 3.5 times 2 is 7, and the 14 should be 4. And now that 4 will go in there for that A. Twelve is my mass, my acceleration is 4, and I get 48 newtons. Isn't that a beautiful solution? Things are nice up and down, right? Left to right. It explains exactly the steps that I went through.
What's newtons? Like
What's newtons? Newtons is the unit of force.
Okay, but is it always going to be kg times meters?
Yep. Mhm.
You're not going to use any other mass.
One Newton is defined to be 1 kilogram meter per second squared. It's a definition. It must be in kilograms. What you're really asking is, does this have to be in kilograms?
Yeah.
And the answer to that is yes. If I give it to you in grams, you must convert to kilograms. Good question. There's a 3-mark question, nice and arranged, okay? It shows me your process. That's what I need to see. Okay, that's what I need to see. Okay? Good? Yeah? Oh, okay. I would like you to draw a free body diagram for this while I go do my attendance. A 100 kilogram crate, at the very least, write out what you know and write out what you're trying to solve. Okay? And maybe draw me a picture. When you draw pictures, you have to sort of realize what your frame of reference or what your viewpoint is. The previous one, let's just go back here a little bit. The previous one, did I even draw a picture on that last one? I didn't. Okay? But you're right, Alex, it's a side view. Let's just, maybe we should draw a picture for that person. I probably should have, right? Have you got room to draw a picture, do you think, for the first one still somewhere? Okay, so Alex is right. It's going to be a side view, right? It's a constant force like this. We have some applied force. There was no friction. We have a weight force. We have a normal force. The weight force and the normal force, basically, we could ignore because they cancel each other out. They have no effect on it. We wouldn't say they're negligible because they're there, but they have no effect, right? Alex is right. We're looking at it sideways, right? This one, I have one force being 250 newtons south and 150 newtons east. So am I looking at it sideways? Like, am I looking at it like this? No, I'm looking at this one from above, like a bird's eye view kind of. So there's two sort of scenarios, right? So you should have a 100 kilogram crate, and you should have 250 newtons down, and you should have 150 newtons east. Is that what you have? Good. Now, which way is the thing going to go? Southeast, but more to the south, right? South, southeast. Kind of like that, right? In fact, if I'm adding these vectors, like I should be, let me just draw these a little bit better. Okay, if I go 250 newtons is like that, then 150 might be kind of like that. And if I'm supposed to add them tip to tail like you're supposed to, then that's the direction that it goes, right? Now, this is the free body diagram. The vector addition diagram would look like the one I just had. Okay? Basically, you take the free body diagram and then you add the vectors tip to tail. Now, is there any friction?
Yes.
There is friction. Which way is friction going to be?
Northwest.
North, northwest, says Sean. Why is that? You're right.
It's more south. It's stronger cold south.
Okay, back up even more. Why is it to the north and the west?
It's opposite.
Opposite the motion, exactly. I'll put it in blue. Okay. It would be like that, right? If I'm doing my actual vector diagram, then that's blue, which should be smaller. Here, let me just make it a bit smaller. Whoa, that's no good. Let's make it about like that. This would actually go where? If I'm doing my vector diagram. It would actually be like that, wouldn't it? right? And then my overall resultant, my overall net force would be this little guy here, right? There's the 250 down, there's the 150 right, there's the friction force. If I'm to actually label these, that'd be the 250, that'd be the 150. This one would be 50. Now, can I just go 250 plus 150? Well, that's 400 minus 50, 350. Why not?
Well, because
Would sure be nice and easy.
Wait,
Can I just go 250 plus 150 is 400 minus 50, 350?
no.
How come?
Well, like, can you?
No, I can't.
No, you gotta go A squared.
Exactly, because the 250 and the 150 are in opposite directions. I have to add the direction as well. They are vectors. They are vectors. Now, the question actually asked for the acceleration. To get acceleration, I'm going to need F net is equal to ma. Why did I write it way over on the right there?
You gotta do that.
Because I know I got the mass. I know that I don't have the net force. I'm going to have to figure out the net force first. Now, how am I going to find the net force first? The net force is the sum of all those forces. These ones I'm going to have to add by Pythagoras, which I know you learned in grade 8, and I know that because I helped my grade 8 student at home last night with that. And then I'm going to have to do what with the 50? Subtract it. Exactly. Subtract. So I'm just sort of giving you the root there, what we have to do. All right, so step number 1, what are you going to call this red one here? Like this is 250, this is 150. What am I going to call that? I need a name for it.
Force. Maybe force something.
Is it truly the net force? Not technically, because the net force includes the friction. Let's call this one F1. And let's call this one F2. Can we just call this one FA? Like it's the overall applied force. Is that okay, you think? Let's call it that. Okay. So now I'm going to write FA squared is equal to 250 squared plus 150 squared. And solve for FA. And I'm hoping, can I just like put an answer? Like you guys can solve that. You've seen enough of this that you can just do that. Yeah, I'm hoping. Okay, I know that in grade 8 you can't. But so you should get an applied force of 291.5. Okay, so the 250 and the 150 add up to 291.5. Good? Yeah? Leroy, you good? Yeah. All right, now I have to take care of the friction, the net force. Now I'm going to write F net. Now, way back on the very first page, you had this formula. F net is equal to FA plus FF. Hold the presses. I thought it was subtract the friction. Did I make a mistake?
Is it because it's something negative?
Exactly. F net really means sum of all forces, right? The sum of them. Add them all up. But the friction force is always opposite the motion, always opposite the applied force trying to cause the motion. So the friction force is actually negative. So I'm not necessarily subtracting friction. I'm really adding negative. Okay? I'm really adding negative. So that's technically correct. Okay, so I'm going to write F net is equal to FA plus FF. Just slide it over a little bit. And then I'm going to write F net is equal to my applied force of 291.5. And then I'm going to write just minus 50. Are you okay with that? Instead of writing plus minus? So my net force is, of course, 241.5. Good? Now I can go into F net is equal to MA, 241.5. My mass is 100. Solve for A. I'm hoping you guys can solve that. 2.4 meters per second squared.
I'm familiar, but instead of the net force, what could be there for a different question? I'm not sure how to ask it.
Yeah, I'm not sure what you're saying.
I'll think of it.
Okay, you let that percolate for a little while. I see a few people have flipped the page over. Are these becoming more challenging word problems from the first unit?
Yeah.
Yeah?
No, yes.
Yeah?
Yes.
I'm turning up the degree of difficulty. Are you realizing that you're going to have to start writing formulas down and organizing your solution? I'm hoping so. Okay. A man is pulling his 50 kilogram son on a 15 kilogram sled across a frictionless ice surface. Yay, it's frictionless. The rope makes a 30-degree angle with the horizontal. We'll come back to that. He applies a 250 Newton force on the rope for 3 seconds. Find the final velocity of the sled and the distance it travels in 3 seconds. Does your gut tell you that this is going to be several steps long?
Yep.
Okay. Should we start with a picture? Let's start with a picture. Can I just use a box for the boy in the sled? Yes. Can I just add 50 and 15 to make it a 65 kilogram object? Yes. I'm pulling with a 250 Newton force, but it's at an angle, and it's 30 degrees with the horizontal. What the heck does that mean? It means that it's up at an angle like this, and this angle here is 30 degrees. Okay? And this force is 250 newtons. We are to find the final velocity of the sled and the distance it travels in 3 seconds. This is the kinematics part, final velocity, VF, and distance. The only way to get to velocity and distance from forces is to go through F net equals ma. I got to get to F net equals ma before I can branch off. The net force. Are there any other forces acting on this 65 kilogram object? Well, there is. There's the weight force, and there's the normal force. Do they matter?
No.
They don't matter. In fact, a lot of books would even probably ignore them, like not even draw them. Okay? We can ignore it. How much of that 250 actually is pulling sideways? All of it, or a little bit less? Or maybe a little bit more? What do you think? How do you know it's less? You just know. Right? You're right, it's the hypotenuse. That's good. If the 30 degrees was even greater, like say it was 60 or 75 degrees, then it would be even less, Nick? It would be, wouldn't it? Right? The more, the flatter this is, if I can make this flatter, then I'm going to use more of that 250, right? And if I make it steeper, well then more of it goes into lifting up and not enough sideways, okay? So the question is, how much is actually sideways? And this is an important concept. This is called the horizontal component, FH. FH refers to the horizontal component. Now, I have not discussed components yet, I don't think. Have I?
No.
Okay. So horizontal component, it's the part of the force that is actually going sideways. Do you think there's a vertical component? There is indeed. Okay, that's the part that sort of does the lifting up part. Components are big in grade 12. Okay, how much is that FH? I have to figure it out first. As soon as you got an angle like this, you're going to know I got to deal with a component. How do I find out how much that side is? Well, this goes back to used to be grade 9 trigonometry, right? Sine, cos, and tan, right? So let me just draw that a little bigger. This is big and back some good memories. 250 newtons. Yes, I can just see the faces are lighting up with excitement. I get to use the sine, cos, and tan buttons on my calculator again. This side is the opposite. This side is the adjacent. Remember all that? And the adjacent one has the cosine or the sine or the tan.
Which side's the hypotenuse?
The 250 is the hypotenuse. So I've got a hypotenuse, I've got an angle, and I really want to know the adjacent, so I'm going to have to use cosine. Cosine is equal to adjacent over hypotenuse. So cosine 30 is equal to, my adjacent is my horizontal component, so I'm going to put FH in there. My adjacent side is called the horizontal component. And my hypotenuse is my 250. FH is going to, now how do I solve that? Take the 250 up, multiply, right? FH is equal to 250 times the cosine of 30. And your answer should be approximately what? Some of you are calculating, but you should know that it's going to be less than 250, right? Like if you get 794, you got a problem. Or minus something, you got a problem. 250 cos 30. 216.5? Can I give you an always rule? Would you like a rule for all this kind of stuff? So that you don't have to go through all that all over the time? Can I give you a new formula? Is the horizontal component always going to be the adjacent side to this angle? Like, if I draw that angle, is this one always going to be adjacent? Absolutely. So is it always going to be cosine? Absolutely. So is there some way that I could rearrange this? How about I take this formula and I say cosine theta, like for any angle, is equal to, if the adjacent is always the horizontal component, and the hypotenuse is always, shall we just say, f, then what is FH always going to equal? Oh, I can't understand. Exactly. Right? FH is always going to be F cos theta. That is a formula and a rule. The horizontal component is always going to be the applied force times the cosine of theta. Always. Are we even at all close to solving this?
No.
We've only just started. We've got one step done. Okay. Now, the good news is we could do a squared plus b squared equals c squared, but we already know this, right? We don't need that. The good news is it's frictionless. So the horizontal component, is there any friction to involve here? No. So the good news is that really, I got some crazy stuff going on there. Probably my answer, right? The good news is that my net force, my net horizontal force, is actually equal to my horizontal component. There's no friction to involve, right? So my net force is actually 216.5. And now that I've got that, now I can write F net is equal to MA, 216.5. The mass of this thing is 65. A is equal to 216.5 over 65. 3.33. Are we getting it all close?
Yeah.
Getting there. We've crossed the bridge. We've got into kinematics now. Now it's all the stuff that we've been doing. We got acceleration. I need to know final velocity. How do I get to final velocity from acceleration? Need the time. Do I have time? I hope I do. Acceleration is 3.33. Change in velocity, time is 3 seconds. Hopefully you can do that in your head. The change in velocity then is obviously 9.99. Does this kid on the sled start from rest? Generally, yeah. So what does that tell me about the final velocity then? It's also 9.99. So part A is done. Now, to get the distance traveled, can I just go 9.99 times 3? Do you have a question, JC? Do you want to know what this 3 dot thing means here?
Yeah, you can go for it.
Is that what you're asking? The 3 dot thing means therefore. When you got 3 dots in a triangle like that, have you seen that in a math textbook before? 3 dots in a triangle just means therefore. Okay? Yeah, I tend to use it.
So that's your final velocity.
That's the final velocity, but I need average before I can get to distance. You got to cross that bridge. You got to go across the average bridge. So, yeah, here we go. V bar equals VI plus VF all over 2. Initial was 0. 9.99 over 2. Can I round 9.99 up to 10? And then divide by 2? Please. I'm just going to call that 5. Now I go V bar is equal to D over T. 5 is D over 3. My distance traveled, 15 meters. Does your brain hurt? Probably should. Your body should hurt after you lift weights, so your brain should hurt after you learn something new. Makes it stronger. You're probably all wondering, how much is that going to be worth on a test, right?
One more.
1, 2, 3, 4, 5.
So one. Something else.
This will be fun. Nobody in class said. Does it make it any easier if I tell you that it's an ice cream truck?
Oh my God, so much easier. Just kidding. Makes no difference.
A truck has a mass of 1,800 kilograms. How much force will the engine need to accelerate it at 1.75 meters per second squared? The friction force on a paved road is 250 newtons. What am I asking you to solve for? What value? What variable? How much force will the engine need to accelerate? Force applied. I'm asking you to solve for the applied force. What do we know? We know the mass. We know the acceleration. We know the friction force. How do I get to the applied force? The only one that has applied force in it is going to be F net is equal to FA plus FF, right? But I don't have the net force yet. Can I get the net force given the mass and the acceleration? Absolutely. So I have to do F net equals MA first. Is that what, did you do that? F net equals MA first? Yeah? Good. Okay, so that's pretty straightforward. That's going to be 1,800 kilograms times 1.75, giving me a F net of 3150. Oh, this is easy. I take 3150 and I just subtract 250, right? And I subtract 250 and I get 2,900 newtons. How many people got that? You're all wrong. I made a big mistake.
That's your,
Alex?
you subtracted the force equation and adding it.
Thank you. Actually, my mistake was not writing the formula. If you write the formula, you don't make that mistake. What did I do here? I just subtracted. That's the mistake. Watch. The net force is 3150. Put it right below it. Put it in the slot. Applied force is what we're solving for. What's the friction force? Minus 250. And now when I solve it, let me do this. Because it's friction, so it's negative. So when I take this to the other side, it becomes positive, right? And so my applied force is, excuse me, 3150 plus 250. Kind of choked up about this. The applied force is 3,400. Don't make this mistake. Write the formula, put the sign in the right place, and do the math, and it will work out for you. Do you see the mistake you made?
No.
Yeah? I hope you do. All right. You should have, if you flip the page, you should have a sheet of some problems there. Okay? You will notice that there's a, what's that thing called there? What's that little box thing there called?
QR code.
QR code. Do you know what it does, Connor?
It'll take you to the internet page.
It will. What do you think is at that internet page?
Answer. So you expect every person to have something
I
to stand?
don't expect you, but if you have one, you're welcome to use it.
If you don't,
If you don't, then I'll provide you with the solutions another way.
Are the answers set?
The solution sign. The solutions. Okay? I would like it if someone would try that out for me, please, actually.